All right, welcome back. So, the idea and the question we have for today is we need to explore where discontinuities occur within a graph if we don't have a visual. For example, if we're looking at the previous example we did, visually, where are the discontinuities? There are skills and strategies to find the discontinuities when you're looking at the graph. But here, imagine if we don't have a graph and we just have a function like this. And this function has a graph for sure. But let's say you're not given it and you need to know where the discontinuities occur. So let's try and explore the ideas of how we could find that. First, let's look at the x values that make the denominator equal to 0. These create discontinuities. So here, what are the x values that make it equal to 0? Well, let's take a look. If I have x squared plus x minus 6 on the denominator, how do I factor the denominator? Why don't you take your time and try and factor the numerator and denominator? Okay? But it should be x plus 3, x minus 2 is on the denominator, and the top should be x minus 4, x minus 2. And notice that, I already had it over here, that here, x cannot be what? X cannot be -3, and x cannot be 2. But let's see what kind of discontinuities occur at those x values. When we talk about the types of discontinuities, at x equals -3, if we were to graph it, which discontinuity will occur? Will it be a removable, a jump, an infinite? What about at x equals 2? Okay, what I want you to do is go to Desmos right now, go to Desmos and graph this and see what happens at the x value of -3 and the x value of 2. What kind of discontinuities do you get, right? So let's plug it into Desmos and graph it, and then when we look at the graph, it should look something like this, okay? Now, let's see. Remember that our discontinuities occur at x equals -3 and x equals 2. Okay? So here, notice that at x equals -3, what kind of discontinuity do we have? We have a infinite discontinuity for this one. So this is an infinite discontinuity. Here, at x equals 2, notice that for us to understand x equals 2, you have to go on your mouse, and if you left click at x equals 2, you're going to see that it says 2 undefined. So here, it's not on the visual of Desmos, but there should be an open circle here. And if there's an open circle like this, what type of discontinuity occurs at this x equals 2? We're going to say that this is, well, let's take a look. Which one will it be? Here, notice that, well, for sure it's not an infinite discontinuity, so is it removable or jump? Here, for it to be removable, does the limit exist? And yes, the limit does exist because it's going to the same y value from the right and from the left. So here, we're going to say that this is a removable discontinuity. Okay? But now we need to understand, when we have a rational function, when will it become infinite discontinuity and when will there be a removable discontinuity? Here, this is the class notes I want you to write down. If we had the other function, what was it real quick? It was x minus 4, x minus 2 was on top, and what was on the bottom? X minus 2 and x plus 3. Now this, please, we need to fully understand this. So watch what happens. Here, x values that make the denominator equal to 0 create discontinuities. So we know there's a discontinuity. There's a discontinuity at x equals 3 and at x equals -2. These are the discontinuities. But here, if a binomial from the denominator cancels out with a binomial from the numerator. So notice that when we factored this, that I could cancel these x minus 2's. It will create a removable discontinuity. So every time you have a binomial and a binomial in the numerator and denominator, if they cancel, you create a removable discontinuity. But if you have a binomial on the denominator and on the top that doesn't cancel, for example, like this x plus 3 doesn't cancel on the bottom, it will always make an infinite discontinuity. All right? So that's very important to understand that. And if you have to, rewatch and re-listen to what I just said for the past minute. But this is going to be very important. What I want you to do is try and look at this graph over here. This idea. Here, for which x values does it make the denominator equal to 0? So we know that x cannot be what? X cannot be 4, x cannot be 1, x cannot be negative 5, and x cannot be 2. So here, the discontinuities will occur over here, right? Now, what kind of discontinuities occur at these x values? Notice that, let's go back. Which ones cancel and which ones do not? Notice that the x minus 4s and the x plus 2s cancel. So we know that at x equals 4 and at x equals minus 2, what do we know? That, remember, let's go back to the notes, that if they cancel from the denominator and numerator, when they cancel, it will have a removable discontinuity. So here, these must be the removable discontinuities. Removable discontinuity. All right? What about at x equals negative 5 and that x equals 1? Here, these two binomials don't cancel. So these must have, vertical asymptotes, for sure. Asymptotes. But they're also going to have infinite discontinuities. All right? What I want you to do is go to Desmos and check to see that this is true once you plug this in. All right? I hope this video helped. What I'd like you to do is, the homework will be to try and practice everything we've done from part 1 and part 2 of this series of discontinuities. For this part of your homework over here on the back, what I want, like here, this is pretty straightforward. You've done a lot of examples of these. Here, what I want you to do for each one of these graphs for your homework, if you have time, is where are the discontinuities, right? What types of discontinuities must exist for those x values? And confirm your prediction by checking it out on Desmos, and then try and express the domain of each of these rational functions. All right? I'll see you in class.